probably our first, well, apart from the definition. So the next difficult thing is this what's called the first shift theorem. So basically it says that so we actually have color here, which is useful. So this here is f of t, and that gets transformed to big F of s. Yeah, okay. Now what we can do is we can take f of t, so this is going to be the red thing, and multiply it by what we're going to call an exponential shift. Now this particular exponential shift is e to the 2t. And what this is going to do, it's going to have the effect of shifting the graph over. And how that works is we'll have this shifted over by 2. So this will be, I'm going to write shift. Try and write shift shifted by 2. So we get the big F of s. And yeah, so basically the story is if you take a function f of t and you multiplying by an exponential shift, so, and the reason we call it an exponential shift is because it shifts over here. So let me write this down. So multiplying by e to the let's see, times e to the, now when we do it in practice, we're going to be using negative exponentials, but just for this explanation, I'll use positive ones. So say multiplying by e to the at in the time domain is the same as shifting the graph by a in the s domain. Okay, so what we're eventually going to be doing though is, what we're actually eventually going to be doing is we're going to be, yeah, sure, we're going to be going from t to s, but we're also going to be coming back from s to t. And what we're going to be doing, and it's going to be very difficult, is recognizing that we have what's called a shifted version of a Laplace transform. And when we have a shifted version of a Laplace transform, we bring it back as if it isn't shifted at all, and then we multiply it by this exponential shift. So say if you're sending back this thing, so you recognize that it's shifted, you bring it back as normal, so the big F of s goes back to f of t, but because it's shifted, you multiply it by an exponential shift over here. I'm not going to pretend that's particularly easy, and would possibly make a bit more sense eventually when we do examples. But there's no two ways about it. You're going to have to be working regularly in this chapter, or otherwise you're going to get completely lost. Because if you already have no idea what a Laplace transform is, this is just complete gibberish. Okay, so let's do a question here. So the way we're going to look at this, so we're going to find the Laplace transform of this exponential times t squared. The way I want you to read it is, it's the Laplace transform of t squared, but the t squared is multiplied by this exponential shift e to the minus 1t. Okay, so what does the Laplace transform say? It says you send it as normal. So and then you replace the s with s plus a. So let's write down a little table thing from the tables. So t to the n is sent by the Laplace transform to n factorial over s to the power of n plus 1. Okay, so what will t squared be sent to? So t squared, we can write down the Laplace transform of t squared if we want. Using this formula is sent to n factorial. So here the n is equal to 2. So that's 2 factorial. I'm going to have to do the fraction like this because of space. Divided by s to the power of 2 plus 1. Now what's 2 factorial? Is 2 by 1 is 2. What's s to the power 2 plus 1? That's s to the power 3. Therefore, the Laplace transform of t squared times this exponential shift is, now what does the first shift theorem says? It says if something is multiplied by an exponential shift in the time domain, do the Laplace transform as normal, but then change from s to s plus a. So send the t squared as normal. That'll give you 2 over s cubed. But because it's multiplied by this exponential shift, you change the s to s plus 1. So see what it does. It says if it's multiplied by an exponential shift in the time domain, send it as normal, but change the s to s. In this case, if it's an e to the minus at, you change the s to s plus a. If it's an e plus at, you'll change the s to s minus a. But most of the time, it'll be a negative exponential. Okay, so another example here. Let's see if we space on the next page. No, there's no space here, so we'll have to be careful. So first of all, we'll write it slightly differently. We'll write it as the function first, the cos 3t, and then the exponential shift. If you want to see why this formula works, it's shown in an appendix if you want to find it. So if we consult the tables, it'll say that cos omega t is sent to, by the Laplace transform, s over s squared plus omega squared. So therefore, if we're doing the Laplace transform of cos 3t times e to the minus 2t equal to, so what do we do? So the first shift theorem says send it as normal, so send it to s over s squared plus omega squared. Now the omega here is 3, so we'll do 3 squared. But the shifting says all the s's must be shifted to, now here because it's e to the minus 2a, they all get shifted to s plus 2. Now it's going to be very, very difficult for us later on, and you can leave that like that, is we'll be going the other way. We'll be doing the inverse, and it'll be very, very difficult. There's no two ways about it. And we'll have to recognize this thing on the right as the same as the Laplace transform of cos 3t, except with the s shifted to s plus 2. So we'll be bringing back the black bit, as it were, the s over s squared plus 3 squared to cos 3t, but because it was shifted to s plus 2, we must multiply the cos 3t by the negative exponential, the exponential shift. We will come back to that again. It will be probably the hardest thing we do. It will involve the hardest thing we do. Okay, so now here it says, oh, can we say anything about the Laplace transform of a derivative? Another way, a kind of a big way of kind of understanding the Laplace transform is, and I'll do it kind of in analogy. So we would have said before that kind of logs, for example, essentially in a kind of a way turn multiplication into addition. Now that notation is you know, it's nonsense, but it can be made, it can make sense of it. In particular, log of x times y is equal to log of x plus log of y. So you can see the logs kind of reduce the complexity from multiplication down to addition. In a similar way, very, very roughly, what the Laplace transform does, it turns differentiation into multiplication with s. So it turns, and this is what the whole chapter hinges on. Laplace transforms make differentiation easy. Now, what do I mean by it makes differentiation easy? What I mean is, if you have a derivative in the time domain, that derivative will turn into just multiplication by s in the s domain. So what that means is that differential equations can be turned, where you have derivatives, can be turned into just algebra equations. So you can turn difficult differential equations in the time domain into easy algebra equations. And that's very, very powerful. Okay, now it's not exactly like, it's not, if I kind of write the similar thing, it's not exactly that, like, how do we write this precisely? So I'll just write something similar to this up here. So Laplace transform of the derivative of little f of t, so it gets turned into s times big F of s. Now the only thing that's missing is this little f of 0. That's, so it's not exactly it's not precisely multiplication by s. There's this little f of 0 knocking around as well. Again, if you want to see where this comes from, there is an appendix with all of these. So it turns out that the Laplace transform turns derivatives into multiplication by s minus this little f of 0. Okay, so let's do an example of this. Right, you have a differential equation here, and what we're going to do is we're going to try and find the Laplace transform of the solution. So at this stage you should understand your job is to find y of t. That's your job. Now what we're going to do is, rather than working with this differential equation with the t, we're going to completely translate the differential equation into, rather than an equation with t's, a differential equation with t's, it's going to be an algebra equation with s's. Now what we're going to do is we're going to apply the Laplace transform linearly to both sides of this differential equation. And I think I'm going to skip one line. So maybe I'll do the first line up here. So if these two things are equal, I can take the Laplace transform of both of them. Okay. And now what I'm going to do is I'm going to use the fact that the Laplace transform is linear. Now what linear means is, if you want to find the Laplace transform of a sum, you can do it term by term. So the Laplace transform of dy dt plus 4y of t is the same as the Laplace transform of dy dt plus the Laplace transform of 4y of t. And also linearity includes the fact that you can take out constants. So the next line after this one is in fact the Laplace transform of dy dt plus, fixing the 4, Laplace transform of y of t is equal to, I can fix the other 4, it's supposed to be 4, Laplace transform of e to the minus t. Okay, so the first thing we got to see, we've got this formula up here. Right, we're focusing on this. Now in the question we're looking at, it's not f of t, it's y of t. So we're working with y of t. So instead of f's in this formula, we're going to be using y's. So like, imagine if this is with a y here, it'll be the Laplace transform of y dashed of t equal to, now the s doesn't change. Instead of big F, it'll be big Y. Instead of little f of 0, it'll be little y of 0. Okay, and remember that dy dt is exactly the same thing as y dashed of t. So now that is written down here as well. So the Laplace transform of the first derivative goes like this. S times big Y of S minus little y of 0 plus 4 times. Now what's little y of t sent to? So we would have spoken about this in the previous lecture. Little y of t, so it's going to be translated from t to s, and to kind of show that it's been translated, we don't use little y of s, we use big Y of s. Equal to 4 times. Now what about this e to the minus t? Well, there's something in the tables that says that the Laplace transform of e to the minus at is 1, we will get these tables to you, 1 over s plus a. So e to the minus t is e to the minus 1t, so it's like this blue thing with the a equal to 1. So 1 over s plus 1. Okay, so that's take the Laplace transform on both sides. Now what we want to find, see now look what you've done. You've turned this differential equation into an algebra equation. So your job now is to solve for big Y of S, but it's just an algebra problem. So you've reduced difficult differentiation to a very easy algebra. Now, one thing we have to do is we actually know the value, we will know the initial conditions. So here it says y of 0 is 1. So this y of 0 is equal to 1, we'll input that. And I'll write this as 4 over s plus 1. Now, just for space, I'll go over here. So you're trying to solve for big Y of S. So what you want to get all the Y of S's on one side. You want to get that minus 1 out of there. So we're going to add 1 to both sides. And so you'll have S times big Y of S plus 4 times big Y of S equal to 4 over S plus 1 plus 1. Now, if you want to solve this for Y of S, it looks like 1 over S, but it's actually Y of S. Now, I'll put you out of your misery here. You can have a think about how you do it, but how you do it is you take out the common factor of Y of S there. So you get Y of S times, and I'm just using a square bracket for no particular reason, S plus 4 is equal to 1 over S plus 1, 4 over S plus 1 plus 1. Now we're trying to get Y of S on its own. It's multiplied by this S plus 4. We don't want that. So what's the opposite of multiplying by S plus 4? Dividing by S plus 4. So we're going to divide both sides by S plus 4. And I'll just write that down, just keep track of it. So we're dividing both sides by S plus 4. If I divide the left-hand side by S plus 4, you'll have Y of S multiplied by S plus 4, divided by S plus 4. The division gets rid of it essentially. It undoes it. So you get Y of S equal to. Now things are a little bit complicated here on the right-hand side, but basically you've got a sum divided by S plus 4. Now the second term is absolutely fine. It's just going to be 1 divided by S plus 4. Now the way I want you to think about the first one, and this might end up being questions if you're properly doing your weekly kind of homework and getting feedback. What you have here is 4 divided by S plus 1, but now it's also divided by S plus 4. So you had 4 divided by S plus 1, now it's also divided by S plus 4, and that's it. Now the job from here isn't so easy. So essentially you've taken your differential equation, you've translated it into an algebra equation, you've solved the algebra equation, and now what you have to do is you have to translate back from S to T, and that won't be easy. We have a similar story with second derivatives, and although we won't be using them, there's formulas as well for third derivatives and fourth derivatives, etc. Essentially what it does is the Laplace transform will turn the fifth derivative roughly into multiplication by S to the 5. So it turns difficult differential equations into algebra equations, which we know how to solve since we were in secondary school. Okay,